In this video, I'm going to show some specific tools to solve some specific kinds of partial fraction decompositions quickly and efficiently. We're also going to solve multiple practice problems to show you that it works. Let's get right into it.
Okay, so the first thing that we have to know is that what are the types that will satisfy the thumbs up rule or that can be easily solved with this rule. So let us take an example. Let's say that we have a expression just like this, and we're going to have to split this expression into its partial fractions. So whenever you see in the denominator there are linear factors, or there are factors that will be reducible to linear factors. So in these two cases, we're going to approach with the thumbs up rule. We're going to see another example of the thumbs up rule. So first of all, what are the reasons that we apply thumbs up rule? The reasons are that in the case of a linear factor, or in the case of factors that are reducible to linear factor, if the denominator of the given expression consists of these types of factors, then we're going to apply the thumbs up rule to solve the partial fraction problem efficiently and quickly. So what actually is the thumbs up rule and how do we use it? So let's say this is our expression and we want this expression to be split like this. So that makes sense because we want our expression to be split into the partial fractions just like the right hand side. So there are three unknowns on the right hand side, which are a, b and c, and we have to determine these values. So in order to determine the value of a, that's the thumbs up rule I'm talking about right now. In order to determine the value of a, we're gonna have to put s is equals to -1 on this expression right here, excluding the s plus 1 factor, because if we put s plus 1 factor and we input s is equals to -1 here, so this factor is going to be -1 +1, which is 0. So this entire expression is going to become undefined. We want to find the coefficient of the factor s plus 1. So that's why we will exclude this factor and input s is equals to -1 in the remaining expression. Okay, so if we input s equals to -1 in the remaining expression, what happens? 2 -1 whole square -4 -1 -2 times -1 -3. So the resultant is numerator is going to be -2 and the denominator is this is -3 times -4, which is +12. So it's going to be -1/6, and that is the value of a. It's really easy, right? All right, so now for the value of b, how will we determine the value of b? It's the same system. We have to put s is equals to 2 in the entire expression except s -2 or s -2, because we want to find the coefficient of s -2. That's why we're going to exclude s -2 and input s equals to 2 in the resultant expression. So if we do that, what happens? S equals to 2. We are inputting s equals to 2 here, so 2 whole square -4. Okay, so what does it become? It's 4, and so the expression becomes -4/3. I might be wrong in my calculations. Let's hope that I am not. And for determining the value of c, we're gonna have to input, you guess it by pausing the video, what is the value of s that will lead us to c? Yes, you are probably right. S is going to be 3, and in the same way we input s is equals to 3 in every factor except s -3. All right, so the value of c becomes 7/2. I hope my calculations are correct. So we have determined all the values for a, b and c. So the resultant expression, this is going to become, and that's your answer. So it's really easy, and it was really easy to solve, and the solution is really small. So this is the first case of using the thumbs up rule. Let's look at another case where the denominator is reducible to linear factors. All right, okay, imagine we're dealing with this partial fraction right here. First of all, we're gonna have to check if the denominator is reducible to linear factors, because all the other methods of solving a partial fraction is really complex and they require a lot of effort and time and energy than the thumbs up rule. So we always have to ensure that the thumbs up rule is our first priority. we have to check if the given partial fraction or if the given expression goes under the thumbs up rule type. If it does, then all the other rules should be excluded, and we should always follow the thumbs up rule. So let's see how the denominator, which is this one, is reducible to linear factors. So we can easily, x squared minus 4, we can easily break it up into these two beautiful factors, and thus we can write the resultant factor like this. So now if we input that into this expression, our expression becomes x plus 1 divided by x plus 2, x minus 2, x minus 1. So with this expression, we know that this is going to follow the thumbs up rule because these are all linear factors and we can easily calculate with them. So let's solve this question with the thumbs up rule. Okay, so our first step was writing it. All right, so we have taken this expression and we have written it in the splitting form of the partial fractions. So we know the drill that in order to get the value of a, we're going to have to put x is equals to negative 2 in the whole expression right here, excluding the x plus 2, because we want to find the coefficient of x plus 2. Okay, so plugging in x equals to negative 2 in the whole expression, that results in, okay, my calculations say that it results in a is equals to negative 1 by 12. So we got the value of a. So similarly, we're going to get the value of b and c. For b, we're going to plug in x is equals to 2 in that expression, excluding x negative 2. I am saying this repeatedly because this is a common mistake every student does while performing with the thumbs up rule. This is a really easy rule, really easy to find the solutions, but if you make that mistake, you're going to waste a lot of time. So that's why I'm repeatedly saying that. So plugging in x equals to 2 in the expression, that results in, okay, my calculations say that these plugging in x equals to 2 results in b equals to 3 over 4, and then plugging in x equals to 1 for the value of c, we get, all right, so the value of c is negative 2 over 3. So our whole expression, we have found the values of a, b, and c. So our whole expression, let's write it. The whole expression is going to become negative 1 by 12 x plus 2. The value of b is 3 by 4 times x minus 2. The value of c is negative 2 by 3 x minus 1. And that's the answer. So the conversion to partial fraction, these maths can come in MCQs or multiple choice questions also, where you don't have that much time to solve a partial fraction. So in order to find these coefficients effectively, you might want to use the thumbs up rule for the expressions with linear factors or expressions reducible to linear factors. I hope that much was clear. Okay, so now we're gonna talk about our second rule, which is the cover-up rule. Okay, so what is the cover-up rule? The cover-up rule works for a specific type of partial fraction expressions. Let's look at a expression like this. Let's say that you were given an expression like this. So in the denominator, if we look closely, there are linear factors, but there is a specialty. This one has a to the power 3 over it. So this is going to have repeated roots. It's going to have repeated roots because it has to the power 3 over it. So it's going to have repeated roots, or it's going to have multiple roots. X minus 1 whole to the power 3, this is going to have repeated roots, and in case of repeated roots like this, we're going to use the cover-up rule. What is going to be the formula or the format of the partial fractions that we write? For the linear factor x minus 2, we're going to write a divided by that. For the repeated roots x minus 3 whole cube, we're going to have to write b divided by x plus 1, c divided by x plus 1 whole square, and d divided by x minus 1 whole to the power 3. So for repeated roots like that, we're gonna have to write it in the format of that. Suppose that another expression was like this, x minus 1 whole square times x minus 2. So in that case, we would only write the first expression would be the same. The second expression is going to be x minus 1 plus the third expression is going to be x minus 1 whole square. So in case of repeated roots, divide the partial fractions, and for this part right here, we're going to have to progress to the higher degree by starting from the lowest degree. So starting from 1, we gradually go to the highest degree, summary that is given in the expressions. For example, this one is right in front of you. So this one has the highest degree of 3, so we started with the lowest degree 1 and then we progressed up to 3. So this is the rule for writing the partial fractions in case of repeated roots in the denominator of the given expression. So the cover-up rule works for repeated roots in the denominator. There is going to be a linear factor, of course. If you can't convert it into a linear factor, then that will not follow cover-up rule. It's going to have a linear factor, and the linear factor is going to have repeated roots, and that's how you know that you're going to have to apply cover-up rule for this. So what actually is the cover-up rule? The cover-up rule is like a mix-up of thumbs-up rule and it's the new rules of its own. So first of all, we're going to input for finding the value of a. All right, so my calculations say that by plugging in x equals to 2, we get a equals to 4. And we can also plug in x equals to 1 to a certain extent. Let me say which value are we gonna receive when we plug in x equals to 1. We're gonna receive the value of d here for x equals to 1. Okay, so the question might arise that why are we getting the value of d when we plug in x equals to 1 in the expression, in the left expression. We'll see that in a second. First of all, let's determine the value of d. All right, so plugging in d, my calculations say that d is equals to 1. Okay, why did we get the value of d? I'm going to say that in a second. So our expression becomes a, which is 4 divided by x minus 2. Okay, so we can't use any of the values anymore because the value x equals to 1 is repeated. We can't use x equals to 1 anymore. We only get the value of d while using x equals to 1, and we don't have any more values of x left for determining b and c, as they are the case of repeated roots. So what we do in this case, what we're going to do is that we're going to take into mind that this is a equation along with an identity. I mean, this is an identity. What is the difference between an equation and an identity? An identity is valid for all values of x. An identity is a type of equation that is valid for all sorts of x, and an equation is a type of equation which is valid for only certain values of x. So an equation is not valid for all values of x. Okay, so as this is an identity that we have denoted by writing a triple line there, so we have denoted that this is an identity, and we can input whatever x we want to input in this equation, and then we can get valid values for the expressions for the unknowns b and c. If that sounds ridiculous, let's input. We can't input x equals to 2 or x equals to 1 because those are the identity values we have already used that lead to the values of a and d. So we're going to have to use any other values than 2 or 1. So if we use x equals to 0, for x equals to 0, the left hand side of this equation and the right hand side of this equation is going to be valid because of the fact that this is an identity. So putting x equals to 0 in the left hand side becomes 0, and the right hand side is going to become okay. So this is the format of the right hand side. So we get negative 2. We get the first equation is that negative b plus c. This is the first equation. All right, so this is equation number 1. For equation number 2, let's plug in x is equals to, we have used x is equals to 2 and 1, so let's plug in x is equals to negative 1. So what happens when we plug in that? For x is equals to negative 1, what we're gonna get is that, so the left hand side becomes divided by its negative 2 whole to the power 3, which is negative 8. So negative 8 times negative 3, so it is 1 over 24. And the right hand side becomes, all right, so this is the format of the right hand side, which comes, yeah, so this becomes, okay, so this is equals to 1 by 24. So the resultant equation becomes, negative 0.5b plus 0.25c is equals to 1.25. So this is the second equation. So by solving the first and the second equation, we get the values of b and c. So solving them, we get the values that b equals to negative 4 and c equals to negative 3. So these are the values of b and c that were unknown to us. So if we plug in these values, our expression becomes, it's going to be x square x minus 1 whole to the power 3. Okay, so that's our answer. Now for the unanswered questions. All right, now time has come to answer the unanswered questions, like why did we get the value of d in the first place by plugging in x equals to 1, and what is the validity of this equation? Well, in order to test our solution, we're going to have to go to the primitive way of solving a partial fraction. So in the primitive way, what we used to do is that we used to write it like that. And then we used to multiply the denominator on both sides, which would lead to this expression right here. So just notice a little bit. If we plug in x is equals to 2, in order, why do we get the value of a when we plug in x is equals to 2 in this equation? This is the primitive way, this is the actual way, the basic way of solving a partial fraction, is that we multiply the denominator on both sides and a resultant expression comes up, and then we plug in the values of x in order to determine the unknowns of a, b, c, or d. So the question is, in order to get the value of a, we plugged in x is equals to 2. Why did it give us the value of a? So if you notice the expression, that in this equation there is x minus 2 here, there is x minus 2 here, there is x minus 2 here. So if we plug in x is equals to 2, then this one becomes 0, this one, and this one. All these three expressions becomes 0, and we're left with only a, which yields that a equals to 4. All right, so now the $1,000,000 question, x is equals to 1. If we plug in x is equals to 1 in the second equation right here, then what happens? So plugging in x is equals to 1 results in x is equals to 0, and notice that there is x minus 1 here, x minus 1 here, excluding the d. So this and this expressions will be 0. We're only going to be left with d. So x equals to 1, d 1 minus 2, so the value of d is negative 1. So now we're left with no values of x. So now what we do, now we equate coefficients. What coefficients do we equate? So which of the coefficients should we choose to equate in order to get the values of c and b efficiently? So notice here for a second that with b there is an x minus 1 the whole square, x minus 1 whole square, so there is going to be a value of x square in this expression, and this one is multiplied with x, right? This one is multiplied with x minus 2. So let me break this. So x minus 1 whole square, that's going to contain x square minus 2x plus 1, and x minus 2, this is x minus 2. So if we multiply these two, we get a value of x cubed, right? Multiplying this one with that one, that relates to x cubed, that leads to x cubed. So b is going to have a coefficient with x cubed, right? Now if we look at a has x minus 1 whole cube multiplied with it. So if we now break it down, this is going to look like this. So if we multiply a with x cube, then we also get another coefficient with a. So if we equate the coefficients of x cube in both the cases, then we get the value of b. Do you get the idea? So now we're going to equate the coefficients of x cube on both sides of the equation of the identity. All right, so in the left hand side there is no x cube, so we can just write the coefficient of x cube as 0, and in the right hand side there is an x cube with a and there is an x cube with b. So we can find that b is equals to negative a, and we know that the value of a is 4, so we can say that the value of b is negative 4, and which is the value we got when we were using the cover-up method. So b is equals to negative 4. Okay, so how do we find c? So notice with c, let's see what's going on with c. So in order to get the value of c, let's say that we multiply these two expressions. So if we do multiply these two expressions, what do we get? We get x square minus thrice x plus 2. So c is going to have an x square with it. So we need to equate x square. So which other values have x square with them? So look at b. We multiplied it in this way. So when if we just multiply these two, let's say what the resultant factor looks like. The resultant factor is going to look like x cubed minus 2x squared plus x negative 2x squared positive 4x negative 2. So let's see what are the x squared factors. There are minus 4x squared with b, right? So b has an x squared coefficient of negative 4b. With a, we can see clearly that the x squared coefficient is negative 3. So x has an x squared coefficient of negative thrice a. Okay, so this is negative thrice a, this is negative 4b, and c has an x squared coefficient of only 1. So if we now equate the coefficients of x square, then we're going to get that there is a x squared here, so it's going to be 1. So 1 is equals to negative thrice a negative 4b plus c. So the value of c is going to be 1 plus thrice a negative 4b. So the value of c is going to become, okay, the value of c is going to be negative 3, which is the value that we have got using the cover-up rule. Here it is. This is the value of negative 3. Okay, so this is the cover-up rule method, and it is going to be used for linear factors with repeated roots. These types of expressions are really easily obtained by the cover-up rule. You can also obtain the equation by you can also obtain the resultant expression by equating coefficients and plugging in the values of x. But as this was a really small expression, so the equating coefficients method might seem easy, but for big maths, for maths with more complex calculations and maths with more tedious calculations, that can be really efficiently solved by the cover-up rule. For example, if we look at a math like this. Okay, so for this example, first of all, let's see if this one falls into the category of using the cover-up rule. It certainly does, because it has linear factors. S is a linear factor, s plus 2 is also a linear factor, s minus 2 is linear factor, but it has repeated roots because of the whole squares. So this is the cover-up rule method. Okay, so we are going to express it in terms of these expressions: p divided by s, c divided by s square. All right, so now you are left with 5 unknowns, and this will be really complex and tedious if you wanted to solve it with equating coefficients method. So we're going to use the cover-up method, and let's see if we can solve this easily or efficiently. Okay, so the drill is like the previous one. First we plug in s is equals to negative 2 in the expression, so we get, okay, so we get the value of x. A is equals to 1 over 8. So in order to find the value of b, we're gonna have to plug in s is equals to 0 on both sides of the equation. So the value of b is half, and in order to find d, we have to plug in s is equals to 2 on both sides of the equation. Alright, so the value of d becomes 1 by 2. Okay, so we have found the value of a, b, and d, and our resultant expression will become like this: 1 over 8 s plus 2, 1 over 2 s, c over s square, d, which is half of s minus 2, plus e, s minus 2 whole squared. Okay, all right, so with this expression we're going to try and solve for c and e. If we wanted to apply the equating coefficients method here, it will be really tedious and complex, and it will lead to more probability of error in calculation. So we're not going to use that here. We're going to use the cover-up rule. So using the cover-up rule, first of all, let's try, we have tried s is equals to 0, negative 2, and positive 2. We have 2 unknowns here, so we need 2 more values of s in order to find those values. So let's say we try s is equals to 1 on both sides. S is equals to, if we try s is equals to 1 on both sides, the expression becomes like this. So the resultant equation is going to be 0.625. This is the first equation. And let's say we try s is equals to negative 1. If we try s is equals to negative 1, the resultant equation becomes, okay, this is the resultant equation. So the final equation is going to be minus 1/3 of b minus d is equals to minus 0.125. Alright, so solving these two equations will lead to the values of b equals -3/8 and d equals, sorry, we're finding the values of c and e, right? So this is going to be c and e. I misplaced the values, so this here is going to be e and this is going to be c. So this one is going to be e and this is going to be c. Similarly here, this one is going to be e, this is going to be c. Okay, so the values of e is -3/8 and the value of c is 1/4, and that's your answer. If you like, you can verify this answer by using the equating coefficients method, and that's a homework that I would like to left behind for you, that you solve this expression with equating coefficients and you match the answers here. If you don't match, that means your equating coefficient methods have contained some mistaken calculations. Okay, so then we're going to talk about the most efficient process of them all. If the denominator has imaginary roots, non-linear roots with imaginary roots, then what do we do? That's the process that we're going to talk about.